All right, let's pick back up. So let me go back and define enthalpy. I feel like we started talking about change in enthalpy, but didn't define enthalpy. I feel like I skipped over that. Enthalpy, I know there's so much new terminology in this section. Enthalpy is the stored energy in something. So we talked about things all have potential energy. That's what the enthalpy is, the amount of stored energy. So everything has its own enthalpy. And then that change in enthalpy, so in that energy is determined by the strength of the bonds in the molecule. That might make a little more sense, hopefully. Hopefully that makes a light bulb go off just a little bit more. I feel like this is a chapter where it's like you hear it, you read it, you hear it again, we talk about it some more, and gradually some light bulbs will go off more and more, and then suddenly you'll have a nice big bright room by the end of a couple weeks here. So we talked about figuring out that change in enthalpy, and whether it's endothermic or exothermic, just to kind of get the big picture here, using those Lewis structures and then the bond energies. But then they said, what if there was a way that we could just know the enthalpy, the amount of stored energy in each part of the reactants and products? We could just then subtract, find the difference between those, like we did with the Lewis bonds, and then we could know whether it was endothermic or exothermic. And that's all that we do from Hess's law. So let's see, they give us, we call this the change in enthalpy of formation. And again, there's another chart of this. And so this is where we're going to now find, we'll do the examples together, but we're going to find basically just the enthalpy of the products, and we're going to subtract, am I saying that right? I believe I am. Yeah, the change in, we're going to sum up all the products and all the enthalpies of those products and subtract the sum of the enthalpies of all the reactants, and we're just going to get this difference. And then if it's going to be negative or it's going to be positive, and it's going to tell if it's endothermic or exothermic. So that's all that's happening there. Against the math, it's just addition and subtraction, adding them all up for reactants and products. So lots of adding and subtracting, not hard math, just conceptually a little bit weird. So we will do that in class, that example on Monday. And then, of course, we're going to apply enthalpy to stoichiometry. Of course we are. It's not really hard. Basically, we are going to get something into moles, and enthalpy is kilojoules per mole. We can, no, it's not. What we're saying when we find out enthalpy, we say there's maybe, let's say if it's endothermic, there's a certain amount of energy that the reaction needs to absorb. This is easier to actually look at in a problem, but if I say in a given reaction, let's say there's 3 moles of oxygen in the reactant in a balanced equation. And so for every 3 moles of oxygen, that amount of energy is needed. So I can use that as a conversion, that like 3 moles is equal to, let's say, 1,000 kilojoules of energy. And I can use that as a conversion to find an amount of energy that's used. And that's how we're going to use that in stoichiometry. That probably sounds super confusing just in words, but I hope when you see it on paper, it won't be too terribly confusing. But your stoichiometry skills need to be strong. So when I said stoichiometry is not going away, I really meant it's not going away. It keeps showing up. So we'll work that problem together, and hopefully that'll make sense. Okay, then they get into some energy diagrams. And because they are diagrams, they're much easier if you look at them. Basically, they're showing some different things. They're showing on a diagram. This will probably be a little easier to talk about in class, but as you look at these diagrams on page 467, so you should always have your book out while I'm talking, so look at page 467, so we're talking about and looking at the same thing. If you look at that particular diagram, you've got energy on that y-axis, and then the x-axis is just showing the progress, like over time, which obviously would be really quick, of the, well, that's not true, maybe not always quick, but the progress of the reaction, that chronological progress. And so we can see in that first example that the energy is very high in the reactants, and then there's an intermediate state they call the activation energy, and then the reaction ends and the energy is much lower. And so they say instead of calculating the change in enthalpy, we could communicate the energetics of this reaction by simply drawing a picture. I wanted to see, let's see. Go ahead and read real well what's on 468. They're just explaining those diagrams and how you can see how the energy, like on the following page on 469, you can see that the energy of the reactants is really low. I'm sorry, guys, my voice is not cooperating this week. And that then the products, then the energy ends really high. And so you can kind of just, that's a endothermic, that second one. The reactants had to absorb a lot of energy to break the bonds. And then products end up higher. That first one was exothermic, I believe. Was that one exothermic? It must have been. So it started up high and then went down low, so energy was released. I'm not a diagram person. You have to work really hard to, people are different kinds of learners. I do much better like reading it, hearing it, more reading a description of it, and showing it in a diagram is super confusing. Not confusing, I can figure it out, but it takes my brain a little bit more energy. If you find that you're one of those kind of people, don't be dismayed. It's just good to be able to put things in diagram form or written form because we all take in information different ways. And sometimes there's things you can see better in a diagram, but that might not be your best mode of getting information. So it may take you a little bit more time to dissect those diagrams, really. Okay, I don't think I have much voice left. Let's see. They talk about activation energy, which is energy necessary to start a chemical reaction. So think about it. I have paper here and I have oxygen. Those could burn, right? But they aren't just spontaneously burning. They need some activation energy, which they could get like in the form of a flame. Can start that. Or just, friction can start a combustion reaction. So they talk about that there. So then we get into entropy. Goodness. I don't know if I'm going to get the entropy video done tonight. I think my voice is going to totally quit on me. Let me see how much more. Let me just talk about entropy very generally. And then you can get more of the specifics of it from the book, because we're going to work problems with entropy. And they're going to be a lot like what I just talked about with that, knowing the enthalpy of an individual substance and being able to figure it out with the products and reactants and subtract and find the difference. You're going to do that same process with entropy. So it's like we did it with bond energies, then we do it with enthalpy, and then we do it with entropy. Same math, same kind of equation, kind of finding the difference between both sides and seeing, is it negative or positive? In the case of entropy, we describe it a little bit differently. Entropy, if you've never heard those words before, is a measure of the disorder that exists in any system. And existentially and physically, truly, we are always moving towards a more disordered state. Because think about it, it's kind of a spiritual thing too. Isn't it funny? Here's where science and spirituality overlap, which they always do, really. Some, if they find my video and are not a believer in God, would not necessarily agree with that. But I would beg to differ. But nonetheless, entropy means that it's describing the amount of disorder in any system. So currently in my living room, I did clean it up, but it is now in a state of disorder as our day has gone on. It moved from a more ordered state to a more disorganized state, a state with less order. Think about it in terms of saying, more order to less order. I think that's going to be helpful. So in the universe, the greatest amount of order existed when it was created, and it's just increasing in disorder as time goes on. That's just what entropy is. And so the second law of thermodynamics talks about entropy and says the entropy is what I just said. The entropy of the universe must always either increase or remain the same. It can never decrease. So entropy means it's correlated to disorder. So disorder is increasing. And then it talks about that in relation to states of matter. And So we talked about solid, gas, and liquid. A solid state has the least amount of entropy, the least amount of disorder. So when you get confused, just really replace the word entropy with disorder. A solid state has the least amount of disorder because the pieces are all right there. They're not moving very much. They're staying all orderly. But as we get to a liquid and to a gas, they're moving around more. That disorder and chaos is increasing. So that's a way you can think about that too. Remember that. And then the entropy of a system increases with increasing temperature, because think about it, that's how our states of mass change, is with increasing temperature. And so that's why that would make sense. Okay, let's see. And the entropy of a system increases as the matter it contains increases. So think about it like if you had a room, they give this example, but it's, I think, a really good one. I don't know why, but I'm just copying it because it's a good one. I'm just restating it because it's a good one. If I have a room where there's not very much stuff, I can put it all away, and that order can be restored really nicely. We don't really restore, well, we do restore order, actually, we get to that, but we have to apply energy to do that. So it's actually decreasing, but we can apply some energy, that's more physics, to get a better, a lesser state of entropy, but it will still descend into disorder without applying energy. That's a side note. I don't think the book actually says that, but that's more of a physics definition, physics concept. But if you have a whole bunch of stuff in a room, it's a lot harder to find a place for everything, so that chaos and disorder is greater when there's more mass. That's just a nice way to think about it, to help you remember that. So if you have a sample of gas that contains 5 moles, that will have more entropy than a sample that has 3 moles, just has more mass. So now they start talking about whether using that concept of more mass, whether a chemical reaction is going from a state of more entropy to less entropy, or so more disorder to less disorder, or vice versa. And basically we're just counting molecules, really. And then they're also talking about, you look at the equation and you say, are the products or the reactants all gases? Because automatically gases have more entropy, so that side is going to have more entropy than the other. Or maybe, so you're looking at that. And then, or if there's all solids on one side and liquids and gases on the other, that's going to help you determine that too. So, and then we're going to have another chart like we've had, chart 13.4 on page 475, where it's got the standard absolute entropies of different molecules. And we're going to do that same thing where we can add up all the entropies on one side of the products and add up all the reactants and subtract and see, are we going from negative to positive? So then they get into a conversation about the proper application of the second law of thermodynamics, that we're always moving from less entropy to more entropy, less disorder to more disorder. And they give an example of, because that would sound like, well, could we have an equation happen where we move from more disorder to less, that are entropy, that make it look like it's going in that direction? And the question is, we can, and it's not in defiance of the second law of thermodynamics. So they give an example. It's not contradicting it. They give an example of a bucket of water freezing. So it's going from a liquid to a solid. It looks like it's going from a more disordered state to a less disordered state. This taxes my brain just a little bit, but it makes sense when you read it. But it's talking about how you have to look at everything in the entire system, and that the very process of freezing is actually a release of energy into the environment. So when something gets cold, it's not that it's losing energy, it's that the environment's absorbing that energy. And so the water loses it to the environment, and so it gets colder and freezes. And so the surroundings heat up. So what happens to a substance entropy when it heats up? It actually increases. Remember, we talked about entropy increases with temperature. So there actually was an increase in entropy. So, so it says, as a result, the total change of entropy, get the right word out, which also is symbolized by an S, doesn't change. So it's in agreement with the second law of thermodynamics, because it says the change in entropy will either be positive or zero. So if overall the change is zero, that's okay too. So go ahead and read that. It's just for those of you that are thinking about that and saying, wait a minute, that's contradicting that second law, and think you've discovered some amazing discovery. Keep thinking those thoughts, but in this case, that is not true. So, oh, Gibbs free energy. I don't think I can do Gibbs free energy tonight. It is, it's not hard, but it's just conceptually like kind of a big earful. So I'm going to wait and make a video on that tomorrow. I know nobody's going to listen to all of these tonight anyway, so there'll just be a third one here to listen to on Gibbs free energy, and that is the last part of this unit. I'm kind of glad. This one's a little tricky. It's not, but like I said, I know right now you're probably thinking it sounds hard, but the math is not going to be hard. We're just going to get things plugged into the right place. So even if some of this stuff doesn't make sense to you, please do not fret. I think that you're going to be able to do the math and the problem's just fine. We're just going to have to wrestle through it a bit. Or maybe you read this chapter and it totally makes sense to you. And if it does, awesome. You're super smart and should be like some kind of amazing engineer. And even if it didn't, you could probably still be an engineer. You might just need a little more time to study it and process it, especially if you're hearing it for the first time. All right, you all have a great night. I will get more up for you. I'm sorry, I don't think I put up extra practice problems on Moodle, but we did talk about it, and hopefully by now you know the routine, so still do it, even though I don't have it there. And I'll get these videos linked into Moodle tomorrow. And your lab write-up, you need to finish that up. So if you have questions about that, ask me. It hopefully was pretty clear in the information you had from the link that I gave you, but if it's not, let's have some conversation about that before Monday. All right, guys, good night. Take care. Bye-bye.